Hi, welcome back to Act 2 of JAX, and this is Lecture 7, High Loop Acceleration. So we're going to continue our exploration of the features and restrictions of JIT within JAX, and today we're specifically going to be looking at porting our loops from Python code to JAX primitives so that they can compile more efficiently because we'll have simpler computational graphs that actually know about the loops that we're doing. So there's the three sort of main loops that come up in deep learning are, well, you could say the loop over layers in the forward class of a deep neural network. And the term deep comes from having like a lot of layers. And often these layers have a similar structure, and so we'd be computing on them with a loop. That's the first type of loop that we see in deep learning. So the second type, you could say, is the loop over the batch dimension when we're computing a batch of inputs all together, although we often do this loop in parallel rather than in series like a normal Python loop. And the third type is the training loop itself, so the loop through all of the batches or all of the epochs that we're going to be using to train our model. Now we've already managed to accelerate the loop over a batch using VMAP, because this loop happens, like I said, in parallel, and VMAP is good at running the same function kind of element-wise over arrays, or in this case, sort of element-wise in the batch dimension, and there may be sort of higher dimensional elements. And today we're going to be looking at accelerating the other types of loops. So the loop through layers of a forward pass, which is a serial loop, and the training loop, which is another type of serial loop, where the iterations need to happen in series because each iteration depends on the state that was computed in the previous one. But before we get started actually implementing a deeper neural network with a loop in the forward pass and accelerating the training loop, we're going to revisit the JIT dojo so that we can learn a little bit more about these computational graphs and JITting loops in JAX. So you can join me in the JAX repository, activate the JAX virtual environment, and let's have a look at lesson 4, which is where we pick up from last time. So this is lesson 4, and I can just go ahead and run. I can run the lesson, and we'll see if we can figure out the output. So let's see what we've got here. So we're first defining a function, and like before, we're wrapping this with the JIT decorator, which means it's going to have, this compilation cache attached, and it's going to do some tracing and so on. And what is this function? Well, the input is going to be an integer array of size n, and so is the output. So we might be doing something like looping through this array, perhaps. We've got some print statements in here that are going to go off at trace time. First, we're going to print out a, which so I guess we'll get a JIT tracer. Yeah, you can already see that. We've wrapped our function, and we're calling the function here. And the first thing that we see during trace time is that we print out a, which is a JIT tracer. So then we have this for loop in Python. And we're going through the indices n, and each time we're going to be doing a print, and we're going to be modifying the value of the array, or because the array is immutable, we'll be using the .at.set pattern to rather than mutating the array, create a new array with a modified value. And it looks like we're just going to be multiplying the value of the array at that point by the loop variable. So importantly though, at trace time, we're printing out something that says we're at this loop iteration. And you can see that happens all 4 times. So this print method this print function gets called 4 times. And each of those times, it's going to end up sort of, this is going to end up inside the computational graph, this modification command. So the computational graph is going to have one node for each of these loop iterations, and I will just be a constant. And so I guess we know, and we sort of saw this in the overture as well, JAX doesn't know about this for loop. It just sees basically straight line code with a whole lot of repeated versions of this command. As if we wrote, one way to think about this for your own understanding is it's as if we wrote out at 0.set a0 times 0, followed by this, but with the zeros replaced with ones, and so on. Oops, 1, and then with the zeros replaced as 2s, and then with the 2's replaced as 3's. And so this would be equivalent to this loop code from JAX's perspective. So I'm going to get rid of that now. Obviously, also we would need to put the print statements. So then we're going to print out the value that we get at the end. Unsurprisingly, it's just an int array, and the result is, as you would expect, we've got, we call this with 1, 2, 3, 4. Things get multiplied by 0, 1, 2, and 3, and we end up with this array. Yeah, all we're doing here is calling the function again, so there's no more trace time, and this just reinforces that these loop iterations were being printed out at trace time, and they're not in the computational graph isn't going to do those print commands. We already know that from previous JIT dojo lessons and our own experience. But we see again that we end up with the values multiplied, and it's as if we've gone through that this version of the computational graph where the numbers are kind of hard-coded. That's basically what the computational graph is going to look like. So I think that should be clear. Now let's talk about what we could do about this in order to tell JAX about this loop. So let's just take a moment to look at the whiteboard and discuss a couple of different options we have for telling the compiler about loops in JAX. So back here, I've set up on the whiteboard a few situations where you might have data that you want to loop through. And so we'll start with the basic one that we've already seen, which is when you want to do a parallel loop, and you would use a VMAP for this. So what I mean by a parallel loop is, let's say we have an array. Here I'm symbolizing this array with like 4 elements, 1, 2, 3, 4. And I have a function that operates on individual ones of these elements. By the way, these might be scalars, or they might be like, this might be a batch dimension of size 4 on an array that has extra dimensions. So these elements might not be scalars, they might be arrays in their own right, or even sort of conceptually like pi trees or something like that. But anyway, imagine we're going to loop through this, and we want to apply the same function to each element, and then get the sort of the transformed version of that element, and form that into a new array. So conceptually, the computation we want to do is something like this. We would run this element through our function, and that would generate a new version of the element. And then we would repeat this computation again for the next element, and so on. I think you get the idea. And there's just one more. So I have to do these in series. I have to do these one after another because I only have so many hands. But there's no reason that on the GPU we can't do all of these all at once in parallel on different sort of parts of the GPU. And so that is what, if possible, JAX will do. We'll be applying this function f to each of these elements when we use VMAP. Of course, if there's too many elements, then it might batch them and sort of do chunks at a time. If there's too many to fit on the GPU all at once. I say GPU, I guess it could also be a CPU or a TPU. And so in practice, this might end up being run in parallel or in sort of partially in series, but conceptually what's going on is JAX is going to figure out how to accelerate it as much as possible. So we're already familiar with VMAP. We've already sort of studied that and used it to save us implementing complex code that manually vectorizes these operations. But this kind of loop is not going to actually help us to do computations like we might want to do for a training loop or a forward pass, where we need to kind of take the result of the first iteration and use that when we're doing the second iteration. So for that, we might want a loop that is more like a for loop in Python, where you can modify the state of the context, the local sort of scope, every time you go around the loop. And so JAX has another loop primitive that is called jax.lax.forI_loop. So for_i loop. And the way this works is you give it a function again, and you give it an initial state, and then you're going to iterate this function, applying it to the state repeatedly. And so it might look something more like this. So we have our initial state, and then we're going to apply the function, and we'll get a new version of the initial state. And then we're going to repeat this process a few times. Well, as many times as you ask, you can sort of say how many iterations you want to do when you call this function. And so this is more like a for loop because this state here can represent the sort of accumulated state of your computation. Every time you want to go around the iteration, you can kind of update things about the state and pass it on to the next iteration. So you can build. However, this can't be executed in parallel. Obviously, because you need to know what the computation at one state is before you can apply the function and get the state at the next iteration. I'll just mention that this is sometimes useful, and another similar function that is sometimes useful is the JAX-LAX while loop. And the difference here is that you would use for I loop if you know specifically how many iterations you want. Whereas, just like in Python, you would use a for loop when you sort of have a bounded iteration that you want to do, and you know exactly what you want to iterate through. Or you have, well, I guess you could also have an iterator that is indeterminate, but that's a bit different. This is a bit like for I in range, I suppose, where you would put in the range bounds that you want. Now, if you have an unbounded serial loop, where it's indeterminate when it's going to finish, then you want to use jax.lax.while loop. And this is going to have the same computational structure. However, you're also going to provide a predicate that you're going to check on the state at every step. And if it returns true, then you'll continue the iteration. So again, true, continue, true, and then eventually, if your predicate returns false, the iteration will stop. Just like a while loop, you have a condition at the start of the while loop in Python. And so this is another primitive you can use, and we won't use this today, but we will have a chance to use this by the end of the HiJAX course. This is going to come up later. Now, there's one more general type of loop that is going to kind of combine both the parallel and the serial, and it's actually one of the most commonly used looping primitives in JAX, and that's jax.lax.scan. And this we saw a little bit of a preview of in the overture, but let me just sort of explain the fundamentals of what's going on with jax-lax-scan. This is a combined serial and parallel loop, and it also resembles a fold if you're familiar with the concept of folding from, say, Haskell programming or something like that. So with a scan, we're going to look over here. We're going to have an initial element that we're computing on, just like in the serial loop, and we're going to call this a carry because it's going to be threaded through our computation. We're going to carry it from one iteration to the next. But we're also going to have a range of inputs, just like in the VMAP case, and we want to iterate through each of these inputs. And so you can visualize this, the computation that's going to go on as follows. We apply a function f that is going to take both a carry and an input, and then it's going to produce a new version of the carry, which I can put here, that it computes based on these. And then we're going to repeat this again. And so we have the next input and the new carry, and we're going to apply the function f, and it's going to produce a second modified version of the carry with all of the updated state. And then we do this one more time in this example because we had three things in our three inputs available, and that's how many times it's gonna work. And then the output is going to be this final carry. But actually, there's one more output. It's jax.lax.scan is pretty flexible, and one other thing it allows you to do. This function f is actually supposed to return two things, not just a updated version of the carry, but also some output that is sort of emitted at that particular iteration of the loop. And so I can indicate this by saying there's another output from this, and I'll draw it here as this output element. And each time we call the function f, we're going to have one of these. So there'll be another two values. And then the final output of the scan operation is going to be both this sort of array of outputs, which looks pretty similar to the VMAP that we had at the start, where we had an array of elements coming in and a transformed array of elements coming out. But we've transformed these elements in a way that allowed us to thread this carry through, and we're also going to return the final value of the carry. And so you can use this scan operation to do anything you could do with the for I loop, or actually also the VMAP, although if you don't need to thread a carry through, then you might want to use a VMAP because it will be more efficient to avoid calculating in series what you could calculate in parallel. Anyway, scan is the most common type of loop operation that we're going to be using in our JAX code. So now I think we're ready to get coding. So let's leave the dojo and let's go to lesson 7, or lecture 7, lecture 07, I should say. And so what we have here is this file resnet.py. So I can open that, and we're in lecture 7, high loop acceleration, and it says our demonstration today is to implement a deep, dense residual network for our MNIST digit classification data set. So at the moment, this is an incomplete file, but let me show you around, and then we're going to fill it out. And you can follow along once again in the JAX GitHub repository, where you can find the sort of blank version of this file that we're going to be filling in. So we have our imports like previously. The one thing that I've added here is tqdm, which is for progress bars. I'm sure many of you know this library. We have JAX typing. We're going to be using some various types today. I'm going to use NumPy a little bit later because it will be useful for visualization. But all of our computation is going to be happening with JAX NumPy and JAX, like previously. And I've also got this lightweight JAX library for computing principal component analyses of data, which I'm going to use for a visualization later. So that's installed already in the JAX virtual environment if you followed the installation video. Okay, so we have a training loop here where, normally we've been writing the training loop, but we've worked with this training loop already, basically the same training loop for our convolutional neural networks, and there's no differences here. So let me just walk you through it to bring you up to speed. We're loading the MNIST data. We've done this many times. We're initializing a model. This is new, this DenseResNet class, which currently doesn't exist, but we're going to implement this, and we're going to use our normal API with a init method that's a static method that is going to give us a randomly initialized model. And then we have our optimizer, which we implemented in a previous lecture as well. The Atom optimizer, this is just going to make the optimization a little bit smoother. We've got some hyperparameters coming in, the learning rate and the exponential smoothing parameters for the moment estimates. Okay, then we've got a training loop, and this is a Python for loop using tqdm trange, and that means it's going to give us a progress bar automatically, that's all. It's just like saying range num steps. And we've got familiar by now, we're sampling a batch, randomly choosing a subset of the data, and then getting that subset to be these x batch and y batch variables. We're going to use a batch cross entropy loss and jax.grad to calculate the gradient. I'm not tracking the loss and visualizing the learning curves today because that's not the emphasis, but we will do some other visualization later. Anyway, then we compute the updated state of our optimizer, our Atom, our sort of stateful moment tracking optimizer, and we get a delta, which has previously been called updates for the model. And then we've seen this before, we get the new version of the model by tree mapping JNP add to add these deltas to the model weights. Okay, so that is all sort of standard, other than the fact that there's no visualization code here. But once we implement this DenseResNet so that we can initialize it, we'll be able to run this training loop, and it will train with a progress bar, and we'll see what happens. As for the rest of the code, we are going to need to use this affine transform, which we've already implemented. So to save writing it out again, I'm just starting with this. But we've seen this before. This is just computing the. I'm using a slightly different function here. Just because I implemented this at a different point in time, to implement the reciprocal square root of the number of inputs as a bound for a uniform initialization of the weights. And the actual forward pass itself is just going to be for a single input, and we'll VMAP over this later, the weights times x plus the bias vector. And we've seen this many times now. So we'll be implementing this DenseResNet, which basically stacks a whole lot of these affine transforms together with some nonlinearities as well. We've got our Atom optimizer here, which we sort of implemented painstakingly previously. I'm not going to sort of go through the details there because we've already seen that in a previous tutorial. Likewise, we've got this cross entropy and batch cross entropy, which we've done to death by now. And that's all. So there's also no visualization code. We're going to write some visualization code later. But let's get started. The thing that we need to actually run this code, at the moment, we could try running it, but I think we'll get an error saying this DenseResNet is not defined. We better actually define that DenseResNet, and just going to copy here the code for making it a pie tree and a data class, and then we're going to get started. So class DenseResNet. So ResNet, if you're not familiar, is a term from deep learning to mean a residual net, where basically the output of each layer is added to a residual stream rather than being computed, rather than replacing the output of previous layers. It's kind of appended to it using addition. And that is going to mean that gradients flow a little bit easier back to the early layers in the network, because they have this sort of straight path. As for the DenseResNet's parameters, what we're going to need to do is take our input, which remember is like an image, like a 28 by 28 image for MNIST, and then we're going to need to transform that into a embedding vector that is going to be the start of our residual stream, and then we're going to want to apply many different affine transforms to that, and then add the results of those affine transforms back to the residual stream. And then we're going to want to unembed this residual stream into a prediction, which is going to be logits or probabilities for the 10 classes. So the components of this network are going to be what we'll call an embedding layer, which itself is going to be an affine transform. Then we'll have our actual layers that we're going to do, our residual layers, which I'll call this layers. And for now, I'm just going to set this to be a list of affine transforms. But we're going to work on that later and turn this from a Python list, which is going to correspond to a Python for loop, into a JAX array of parameters with like an extra depth dimension to the parameters, and that is going to help us accelerate this. But for now, we'll just do it like this, and then we'll talk about the unembedding, which is also going to be an affine transform. So this is going to be our network. Let me write the forward pass, and I'll just preemptively try to jax.jit it, because that's where we're going to want to go eventually. And so we'll be keeping in mind when we're writing this to make sure that it's like JIT-friendly code. And so the input here is going to be obviously a self, which is our actual parameters here. This. Oh, by the way, it's fine to have a list here because when we register the data class, that just, remember, a list is just a pie tree. So this is just going to be a fixed size number of children within one of the fields of the data class. Is just going to be like another sort of nested, it's like nesting another data class or something like that, like affine transform itself. So this is totally going to work fine with the data classes. But anyway, or with the pie tree, I should say. Anyway, the actual image that we need input is going to be a float array, and it's going to be our sort of standard MNIST shape of 28 by 28. The output here should also be a float array, which we're going to sort of take to mean the probability predictions, and I believe that should be therefore of size 10. So what we need to do is, like I said, we need to sort of get this 28 by 28 image into a residual stream. And I'm going to say that our embedding transform, I guess I haven't sort of talked about the shapes of these transforms. We would normally do that in the initialization. But let me sort of add some comments here to sort of think that there are 784 pixels in a 28 by 28 image, and I want this affine transform to take us from 784, which will sort of flatten, because we're doing a dense ResNet rather than a convolutional ResNet. I guess that I should have said that. We're going to take this 784 dimensional vector, and let's just use a residual dimension of 128, which will keep things nice and speedy for us. And then each of the affine transforms in this list should be 128 to 128. We need to keep the same size so that we can add the output of each residual layer back into the residual stream. And so if you like, this is like we're going to be going 128 to 128 to 128 to 128 many times, however many times we have in this list. And then our unembedding is going to need to be from 128 dimensions down to 10 dimensions. So this is going to sort of, we can keep this in mind, but actually we'll handle that when we do the initialization. For the forward pass, we actually don't need to know that. We just need to know that in order to get the image from a 28 by 28 vector to a 784 vector, we're going to need to use something like flatten or ravel. So let's jnp.ravel this image, and that will give us a 784 vector. And so then we're free to apply our embedding transform, so self.embedding, which is going to have, it's an affine transform, so it's going to have a forward pass function, and so I can just call that. And let's do a nonlinearity as well, which I think we're going to use tanh. So you could use maybe ReLU if you wanted. However, because we're going to be doing a very deep network, we need to be very careful with our initialization or do some kind of normalization after each layer. And tanh is just going to keep things nice and nice with a nice scale because it's bounded. And so we're going to start with that. And then if you wanted later, you could implement a version of this that uses ReLU instead and add some normalization, or be careful with the initialization. Anyway, so then we're going to implement the actual layers. And so just to get started, we're going to do this as a Python for loop, and we'll come back later and accelerate this. I just want to have a basis of the actual computation that we're trying to accelerate before we go converting this into a JAX style loop. And then we'll have sort of a baseline and we know what we're kind of aiming for. Let's just get this running. So we're going to want to calculate a sort of a residual and then add this later to the residual stream. So let's start by taking layer.forward. Obviously, we've gone through this as if it's just a list, which is what it is, so that's fine. So layer.forward of x, which is going to be the current sort of input or the current state of the residual stream. Then we're going to want to do some nonlinearity. So let's say r is equal to jnp.tanh of r. And now we've got the output of this this step of the residual computation. We better get the new value of x by adding this value of r. And of course, it would be nice if we could do maybe plus equals or something like that. But due to immutability in JAX, we have to do it like this. We're overriding x with the new value where we've added in this r. Okay, so this is going to end up being quite a simple forward pass here because we're nearly done. The only thing we need to do now is unembed our 128-dimensional vector into a 10-dimensional vector and then convert it to some probabilities. So let's apply our unembedding transform, self.unembedding.forward of x, which is our final result of our residual stream. This is going to give us, actually, I could call this logits. And we want to return probs. So why don't I just do jax.nn.softmax. We've seen this before. Not software, softmax of the logits. And then I'll return these probs. And that fulfills the typing contract that I sort of set up here, where I wanted it to be a float array of length 10. And this unembedding is going to give us back size 10, and then this will preserve the size, and that will be what we want. We just have to remember for the loss function is set up to interpret these values as probabilities already, rather than log probabilities. Okay, so we also need to initialize, and so we're going to want to implement a static method, and then jax.jit that, just to keep things nice and speedy, and so we'll and remember that you have to put the JIT after the static method in the file, or like conceptually you have to wrap in JIT before you turn it into a static method, because you can't JIT something that's already a static method. But anyway, we want our init function, and this is going to take a prng key array called key. I don't think we're going to provide any other inputs. I'm not going to make the sizes, the depth of this network, or these embed dimensions parameters, because I want them to be hard-coded at the moment. And next lecture, we're going to look at what it takes to make those parameters, because we'll have to flag them as static for us to be able to JIT. But for now, we'll do it like this. And initializing this is going to be not so straightforward as previous ones, because we have to initialize this entire list of affine transforms. So we're going to need to initialize many affine transforms all at once. I can do this though. I think I'm just going to need 3 keys, and I can then sort of sub-split the key. I can use K1 for the embedding, K2 for all of the layers. I don't want to use the same key for each layer, but I can further split this key. And then K3 for the unembedding. So jax.random.split, and as long as I put in my key and say I want 3 copies, I want to fork this into 3 keys, that will work. And now let's see, I want to return a DenseResNet, and it's going to do this, I need to provide the three components. So an embedding, a layers list, and an unembedding. So the embedding and unembedding is kind of easy. I'm just going to give an affine transform dot init, and I'll give it my k1 that I prepared, key equals k1. Now an affine transform init also expects a num inputs and a num outputs. I know what those are. We already decided up here. It's going to be 784 to 128. So num inputs equals 784 and num outputs equals 128. And I'm just hard coding this. You could make this a parameter after we learn about static parameters later. And then let's skip the layers for now and come back to that after we've done the similarly simple unembedding transform. So it's affine transform.init. And so this one is going to look a little bit like this. So I'll just copy this as a starting point. But we're going to be passing in K3. The number of inputs is going to be 128, and the number of outputs is going to be 10. Okay, so now that leaves us with the task of putting some list here with a whole bunch of initialized affine transforms. So we could do this in various ways. We could go before this return statement and sort of construct a list one by one, initializing these, use a for loop, initialize these affine transforms and append them to a list. I'm going to do it with a list comprehension, which is going to make the code a little bit, a few more lines. It'll be quite a deep expression here for this DenseResNet, but it will be readable enough, I think. The actual entries in this list from the comprehension are all going to be affine transforms. And so we're going to initialize those, and then we're going to basically do this for k in jax.random.split k2, and I don't know how many layers we want, but let's say we want 200 layers, so it's nice and deep, this network. So what this is basically going to do is give me for each key in this, splitting this key into 200 pieces, it's going to initialize a random affine transform parameter and put it in this list. So this is going to have the right shape that we want, and it's a relatively compact way to write the code. And so in order to do this, all I have to do is provide the shape, which is going to be, the key is k from our loop, and the shape is going to be 128 to 128. So that is easy. Okay, and now with this one sort of bit of a messy expression here for the init method, but we've got this list comprehension here, and later we want, this is also a for loop, right? So it would be nice if we could, this is also going to create a big computational graph, by the way. So when we JIT this, when it traces this, it's going to trace through the list comprehension and build a big list that is a big pie tree, and every leaf of that pie tree, every entry in the list is going to be some part of the computational graph. It's going to be a very big expression in the thing that we pass to the compiler. So it would be later we would also like to remove this list comprehension and make it a JAX loop instead of a Python loop. Even though this is a list comprehension, it's still a Python loop. So we'll just mark that as maybe to do, and we'll have to come back later. And I guess while we're adding to-dos, I'll sort of say to do, we also want to remove this loop too. Okay, but now I think, unless there's any mistakes, I think we should now be able to actually run the code. Okay, so there is, I made a mistake here where I moved this to a data folder. So I need to actually put the relative path to the mnist file. Any other issues? Okay, layer and layers, so that's a problem. Yeah, I think I called this layers, but then I called this layer, so that's just got to be layers. Now we're talking. Looks like it's doing something. Initializing the model. Okay, so it took a while to initialize the model, perhaps because this was a big expression. Like I said, this init thing, it's constructing a big thing, and then we're saying it should compile that, and so it might have taken a few seconds to compile this expression with 200 affine transform initializations. That's a lot of commands for every time this is got a uniform transformation and initializing an array. It's a very big program that we asked it to compile. And then it took a moment again to begin the training. I don't know if you caught that. That would have been when it was compiling this loop here, which is 200 long loop. But it didn't take that long to train. Okay, so matrix multiplications, which is basically what this is doing. A lightning fast 128 by 128 matrix multiplications. No sweat for my M2 CPU. So in 30 seconds, we've been able to have many batched forward passes through this network, computed all the gradients that we needed, and we've trained our network. And I think the loss is okay. We're not going to check it. It's not the focus for today. we could make this probably even deeper. It would be interesting to see if we change the depth, is it going to sort of appreciably change the compile time? So, well, what if we go really crazy and make it like 1,000? So 5 times as deep. Then will we notice this take longer to compile? It's taking a few seconds here to compile. It's taking a while. I think it was not taking this long earlier. I don't know what's going to happen here. If it's going to make my computer complain. Should have got the Pro. If I knew I wanted to record lectures, I would have. Yeah, this is going to take a while. Why don't we talk about what's happening next and see how this... you can see that it's taking a longer time to actually initialize the model. That's the lesson that I wanted to take away. So as long as this is not going to eat up enough of my CPU to overload the encoder on the video, I think this is going to be fine. Oh, it's done. Okay, so now it's beginning the training. We should see another delay here as it compiles the forward pass, as it runs through the forward pass, the batched forward pass for the first time. 1,000 layers is not going to take that much longer to actually run. This should take at most like 5 times longer to actually execute this forward pass. But you can see it's taking a lot longer to compile. Okay, but it's done, and then it's faster. Okay, so it is, it's slower. Each pass is slower because we're doing 1,000 computations instead of 200. But the first iteration took the longest, and that was the one where it was compiling, because that was the first time we called the JIT command. So I'll just let that cook for a little bit, and then what we would like to do is be able to run 1,000 layers if we want. It shouldn't be no harder to compile because there's no actual extra complexity. We just change this one number. So this is all a problem of the fact that our loops are in JAX, in Python rather than in JAX. So this is a perfect test bed for figuring out how to use these new primitives. So let's get to that. So I think the first loop that we should look at compiling is going to be, well, we'll stay with the model, and we will probably need to use scan for this. And so it's not exactly obvious how to use scan for this loop, but let's talk about it. So, so what we have here is a computation in Python that is going through each of the layers in self.layers. And for each of those layers, it is doing a forward pass with that layer, and it's computing this this residual sort of addition thing to add to the residual stream, and then it's just adding that, and then this x is going through to the next iteration and becoming an input, and then the sort of base for the output. So I guess the carry should probably be this x, but what about the input? Well, the input is going to be the layer. And if we want to format this for a scan, then we're going to need this layer to be represented, or all of these layers, all of the parameters to be represented actually as a vector of layers with a depth dimension, like I was sort of saying before. So let me quit out of this. We get the picture, I think, that it's going to take a while longer to train. And let me go over to the whiteboard and sort of talk about the pie trees that are involved here. So I can erase all of this stuff about the loops, and we're just focusing on this scan computation. So what I want is I'm going to draw this now going down the board. We have our initial x, and then we want to apply some function to compute a new value of this x. And we want the parameters theta I, the parameters for layer 1 in this case, to come in here. And there's not going to be any output, so we can just leave that out of our drawing. We want this to come out. If we ignore that, I can sort of zoom in on the computation that's going to be going on in this f. This is going to be doing something like r equals forward, or let me put it this way, theta1 dot forward on x, and then we'll do our nonlinearity. So that's tan h of r, and then we'll have our new x equals r plus x, or x plus r. And so that is what's going to go on here. And then we want to do this again and again. And the next time we do this f, we want the next parameter to come in, theta 2 instead of theta 1. And then we'll keep going, and then eventually we'll get the final x out at the end of the loop. And so this is how we're going to use scan, which tells us that we need a version of this function. We need to write this function that is going to implement an individual iteration of this. So it's basically going to be this code here. So let's do that. We can basically take this code and turn this into, well, let me leave this here as commented out for posterity. And we'll write an individual layer transformation, which I don't know, you can call these inner functions like whatever you like, but I like to call it maybe step or something like that. And so the carry should be x, and the input should be layer. And then the output is going to be a tuple of like the next x and the next layer. Sorry, and no output, just the next carry. So x and none. And this x, this is not valid notation here. I'm just typing that in to sort of give an indication of what we're going to do. So eventually we'll have return x and return none. And then I can take this actual code, and this would be our f that we're going to scan over. So to actually do the computation, I would then say jax.lax.scan of step, and then I need to give the initial carry, and then I need to either give a number of iterations or this vector, which we did in the overture, or we need to give a vector of inputs that we have at each point, which is this vector of layers. So I want to put something like layers there. And then the output that I'm going to get is the final carry, which is going to be our x, and then all of the vector of outputs. And so that's going to be nothing. It's going to be just a vector of nones. And so we can just put blank there. Okay, the problem is this layers is a Python list, and we actually need it to be an array. But this would basically work other than that problem. This is all you need to do to actually do the code if we had layers in the right format. So what format should layers be in? Okay, back to the whiteboard for a second. So we kind of need layers to be in a format that is going to be compatible with scan, which means that the first dimension of layers needs to be this depth dimension, and then it can have whatever other dimensions you like, as long as the first dimension is this depth dimension. That's the dimension that scan is going to iterate through by default. So so we need some version of this array that is going to have the weights and biases of scan. The weights and biases of the network as extra dimensions and a depth dimension. So at the moment, an individual layer is a pie tree that looks like this. So it's affine transformation, or affine transform, which has a weights, which is equal to a floating point 32 array of 128 by 128. And then it's a bias, or biases, which is also a floating point 32 array of 128. And so this is sort of the structure of a pie tree that we have. And what we need to do is somehow we need to insert an extra dimension into this pie tree that is going to be the number of steps that we need to do, the number of layers, the depth of the network. Let me move this so that we can work on these types. So the way to do this in PyTree is actually, or in a PyTree, is actually not to think about having an array of affine transformations, but to have an affine transformation of arrays. And what I mean by that is we're going to replace these dimensions. Instead of 128 by 128, we're going to have a single affine transform object. The first part of the dimension will be depth, so this will be like 200, and then 128, and then 128. And then this will be f32, 200, 128. And so this is going to allow us to basically, when we pass this as the inputs, it's a pie tree, and it could be just an initial, it could be just a vector, whatever. We know that all of the JAX API things work with pie trees just like they work with vectors. What it's going to do is walk through this pie tree and provide as input the 0th element of each of these things. And so this is going to mean that theta 1 is going to be equal to an affine transform with the shape weights equals an F32 128 by 128, and then biases equals F32 128. And so that is what we need to go into our code, right? So this is perfect. And that is an example, I guess, of the JAX API and how it sort of just natively does everything with pi trees. And this key idea for today is that when you want instead of a list of pi trees or a vector of pi trees, when you can't really have pi trees as elements of a vector, you instead want to think, let's have a pi tree of vectorized things. And so that's what we want here. And so let's do that in the code. What we're going to need to do is go up here and say this type is not going to be anymore a list of affine transforms. It's actually going to be an affine transform basically of an extra dimension. And so there's not really a good way to annotate that in JAX typing. I wish we could do something like this, affine transform 200 or something like that. And it would indicate that it's like 200 dimensional, but that's not a feature that exists at the moment. So what I normally do instead is I say affine transform 200 as a little comment, and it sort of indicates to me that this is a affine transform 200. And each affine transform is going to be 128 to 128. That's just the notation we can use. Now, how do we actually create this, get our list into this shape? We could do some kind of, we could create the list comprehension. We could do some kind of stack or concatenate with maybe a tree map. You might like to see if you could pull that off if that's the natural way that occurs to you to do it. But an even easier way is going to be to use vmap, because when we're initializing, we don't need to initialize these layers serially with a list comprehension. We can just do it. In parallel, because all of the initialization is independent. And so this is an example of that first type of loop that is a parallel loop where we have a bunch of keys. We have an array of 200 keys, and we want an array of 200 affine transforms, or, you know, it's a pi tree. When I say an array of affine transforms, I mean an affine transform with an extra array dimension. So let's see if we can, instead of using this list comprehension, switch to using a vmap. So what would this look like? Well, we already have this function here, affine transform init, which takes a single key and some shapes as input and gives us back a version of a single affine transform. So why don't we just try vmapping? We can say layers equals jax.vmap of affine transform dot init. And then we would pass in instead an array of keys. So jax.random.split k2 200. We can make this 1,000. There's no reason we can't make it 1,000. Well, the only reason is that I put in the comment up here that it was 200. I suppose I should just generically say this is depth. And then we'll set it to 200 for now, and then we'll set it later to something else. And then we need to still put in the number of inputs and the number of outputs, which is just 128 and 128. Now remember, with a vmapped function, I can only use positional arguments. I can't write them as keyword arguments. And so I need to remember the order of the arguments. But also, I'm not putting in an array of these sizes, so I need to make sure that I'm only vmapping along this first position. So I'm going to expand the vmap and provide an extra argument here and say I want the in axes to be the 0th axis of the first input, and then I don't want a vmap over the other inputs. As for the out axes, this is going to be optional, but we want to specify that the out axis should be a new 0th axis of all of our arrays. Normally, we have our arrays coming out actually as a single array with vmap, but in this case, it's coming out as a pi tree. And so I wanted to just show you that another thing you could do is you could say I want to have an affine transform, and I want the output to be weights 0, biases 0, and this is going to say This is a pi tree. We're not really respecting the types of the data, the ResNet. The affine transform, that's right. We're not really respecting the weights of the affine transforms, the parameters, the fields of the affine transform. We're not really respecting their types because this 0 is not a float array. But it's Python. You can do whatever you like with the types. You don't have to pay any attention to them. The thing this is saying is we can give out axes a pi tree and tell it for each of these things which axis we want for the corresponding part of the output where we want the vmapped axis to go. And in this case, for the weights and the biases, we want it to go at the start of the array. But if I wanted, for example, let's say for some weird example, I wanted this to be 128, 200, and 128, 200, 128. I could do that too. I would just have to put index 1 instead of index 0 here. And like I said, this is optional because if you give vmap a pi tree in full detail, it will sort of work. But if you give it a prefix of a pi tree, which you can view this, it will just sort of map this over everything underneath the root of the pi tree. All of the leaves, it will just use 0 for them. And in fact, that's the default, so we can just get rid of that. But it's slightly neat to sort of show off that you can do it with this pi tree thing, so I'm going to leave it like this for now, but I'm just going to say this is optional. Okay, I'm pretty sure this should work if I get my syntax right, so I need an extra comma at the end there. And then we should be able to get a... okay, something's wrong, so maybe a typo. Yeah, instead of weight, it's just weights, so that's my mistake. Anything else? Okay, yes, there's another thing, and that's just because this layers is, of course, supposed to be self.layers. And so there was no layers defined. I maybe got confused here because I was using the singular layer, but that's once we're inside the scope of this scan, so didn't need self there. Okay, but now it's working. And okay, so I'm not sure if this is faster in the actual loop, because once we've compiled, we're doing the same computations, basically, whether the computational graph was representing them as straight line code or whether it's representing them as a scan. Sometimes I think you might get a small speed up from scanning things, I'm not sure, if it allows JAX to do clever optimizations. But in this case, you might have noticed that the actual compile step here was lightning fast. And so we can wait for this to finish and then show again by taking the example of when it was 1000, where it took a few minutes or like at least around a minute to just compile each of the steps. The initialization, which by the way is now we have successfully gotten rid of this loop, right? Because we're using a vmap instead of a list comprehension. I can do 1000 here and it should still compile lightning fast. There it was. So initialization was lightning fast, and the first training step took not that much longer than the subsequent training steps, which they are taking longer because, and it looks like it's going to take like, roughly 5 times longer. I had 31 seconds here, and this is going to take just over 2 minutes, maybe 2.5 minutes-ish. It looks like this is, as expected, going about 5 times slower because we're doing just more computation. But in both cases, the compilation was lightning fast, and so that is a success. Okay. Now, let me just leave that running because I think it's not a problem. And let's talk about this. I think we've successfully accelerated our forward pass, which is our first of the types of loops that we wanted to accelerate. But then there's also the training loop that we want to accelerate. So let's move on to accelerating the training loop. And accelerating the training loop is pretty cool because it's going to allow you to do things like vmap over different hyperparameters, for example. And do it all accelerated, and so you can do multiple training loops in parallel, which is pretty fun if you have the compute to be able to do that, I suppose. So here we go. So we have another Python loop, and this is another example of a loop that we can move from Python to JAX. And so let me see. So TQDM tRange is going to be a little bit hard to replace because that's like a side effectful pure Python library. There is a JAX equivalent. I can't remember if I added it to the virtual environment. Maybe we'll have to install it at a moment. But let's just ignore that for a second and do TQDM range. Just do range instead of TQDM range. So we're not going to have a progress bar anymore. That's okay. I'm going to close this just in case, so we can run things. Okay, so we've already sort of done something like this. Let's have a look at what this loop is doing and see which of the types of loops it falls into and what would be the best tool for accelerating it. So the content of this loop is going to have an input, which is a step, but I think we're not actually using the step anywhere. We have step later in the code, and we have num steps, but this actual step variable is not used in this loop. So there's actually no input that we need to worry about. There is just some stuff that we're carrying along. So I think we could get away with a for I loop, and this might be a good example to try a for I loop on. Although, if you write the loop in other ways, you might need a scan. So for example, in this case, I'm not actually tracking any metrics. I'm not tracking the loss at each training step. But I might want to track the loss, and then I might want to have it as output. And then you might want to use a scan, because the for I loop is not going to allow you to have actual output. Let me just look over on the JAX documentation at the for I loop. And I've also got the while loop and the scan here in case I need them. These documentation, the JAX documentation, as I've said before, is excellent and is really a good thing to get in the habit of looking up. In this case, it has a very useful Python pseudocode for what the for I loop does. So the for I loop is going to take lower and upper bound. This is like the range that we want. It's going to take a body function to actually represent the body of the loop and the initial value of the carry. And then it looks like what we sort of expect. It's going to sort of start with the value as that initial value, and then it's going to go through a range, a fixed range from lower to upper. So this would be, for example, 0 to num steps. And then it's going to update the value by applying the body function. Oh, it looks like it actually, I forgot about this. It actually does provide the index. So if that is the only thing that we need to, the only sort of input that we need to the body function is the step that we're up to, then for I loop actually provides for that anyway. And then it will apply it to the old value and we'll get the new value. And then once this loop is completed, it's going to return the result. So this is roughly the shape of our loop, and so let's go ahead and do this. So let's change this into a for I loop. So we need to define an initial step. An initial step of the training loop is going to be a function that, what is the actual val here? Okay, so I'm going to contend that it's going to be a tuple. And let me just check. This body function has to take an I and a val. So I can just say I is an int, and then the val, what's the val going to be? It's going to be maybe a tuple, and then I'm going to also return a tuple. But what is going to be in this tuple? It's like everything that represents the state of our loop. So what's changing once we iterate this loop? It's going to be the key. That's going to change. We're going to need to sort of take the initial key and split it to get this key after we've taken off the batch key and used that to generate a batch. And then we're not updating any of the training data here. We're just subsampling a batch that is used to compute the grad, and the grad is just used to compute the delta. Okay, so the opt state and the model, they change. In these lines, they get overridden. So let's say that the val, let's say that the key, opt state, and model is equal to the old val. And then when we return, we'll return the new key, the new opt state, and the new model. And that looks good. And then inside here, we can put what we had before. So now we will sort of get the old val and we'll unpack it into the values of the key, the opt state, and the model. I'm just going to disambiguate this by calling it train step, by the way. Sorry. Then we'll sample a batch. We'll be using this sort of carried value of the key, which came from the val argument. And we will compute a batch, and then we will sort of pass that batch and the current value of the model that came from the updated val. And then we'll get the grads, and then we'll use the grads to compute the new opt state and the deltas. And the opt state is coming from, this opt state here is coming from this opt state, and the new opt state is going to be going out. And then we're going to compute the new, using the old version of the model, and we'll get the new version of the model with the delta, and then we're going to be returning all of these so that in the next step we have, yes, we've carried through to the updated version of these. So this should work, and I should be able to get rid of this, but then we actually have to put in the for I loop. So let's double check here again how we actually call this. So jax.lax.for I loop with this with these values. So let's run the actual loop. Oh, what's the return type? That's something we have to check. I think it's just going to be this value that we want at the end. which we actually, I guess we need just the model from that so we can go on and do some further analysis. We might need the key as well. So yeah, let's just grab all of that. So it's going to be final val equals jax.lax.for loop. I always get the underscore in the wrong place. It's not for underscore I, it's for I underscore loop. And then the lower is going to be equal to 0, and the upper is going to be equal to num steps. That's the loop bounds that we had previously. Let me just remember, the body fun is the next command, and then the init val. So body fun is equal to train step. That's this function that we've written that is of the right shape. It takes an I, which we don't use, but it takes a step index, and then it takes this val, and then the init val. So the init val is equal to the value before we start any of this of key, opstate, and model. Make sure we get these in the right order. Okay. And then this final val, actually, we don't need to call it final val. We can if we want, but you could also just directly unpack this to key, opt state, and model, which will now override what they were before we ran the training loop. So let's see if this runs, although I guess we better make sure it runs fast. So I'm going to go for the 1000 and just for now change this to like 10 or something like that so it runs really fast, because we don't have a progress bar anymore. But we begin training, and we're going to hopefully, in a few seconds, see that it stops. It should be fast. Okay, there we go. So it did run. Okay, cool. So where we're at, we've accelerated the training loop. What I want to know is, can we get a progress bar with the JAX training loop? That would be super useful. And I am going to do this as a live demo where I look up JAX TQDM. And see what the API is, and see if we can use it. Okay, so it only works, it looks like, for maybe scans. Oh no, okay, so it works here. So this is good. So this is going to be a super simple API. I can just decorate my train step function that I use in my for I loop with a loop TQDM and the number of steps, and then it should work. So that is a sort of pretty well designed, pretty simple API. Let's see about that. So I might need to install JAX TQDM. Let me just make sure I get that command right. Yep, JAX TQDM into my virtual environment, because I'm not sure if I've done it before. I'll add this to the requirements file. You won't probably have to do this step because I'll add it later. And then I should be able to import, I guess I'll import it up here, or like replace this import, which we're no longer using. And how do I import it? JAX underscore TQDM. I like importing the library and then rather than importing the individual function. So I'm going to just import JAX TQDM. And then when I'm doing my loop, instead of just train step, I'm going to say JAX underscore TQDM dot for I loop. Is that what it was? Loop TQDM, actually. So loop TQDM. And it looks like it needs the number of iterations that we're going to go through. Yeah, because that's n here, and that's n, and that's n. So we know that. That's just num steps. And so this should hopefully work. Okay, there we go. Hey, it looks like what it's actually doing is pausing every few things coming out of the JAX iteration and then doing a side effect. It's sort of injected these side effects every few steps. And it's sort of not as high frame rate as the regular TQDM because, you know, every time we pause to print, that's taking time, and JAX is all about performance. So the default here is to sort of print a little bit less frequently. I'm confident now that I would be able to sort of see what is going on in the code if we run and trust that it's working if we were to run a much deeper model. So let's see if we go back to 1000, if we can see TQDM, JAX TQDM working. So it's running for 256 iterations. It might wait a while. It might wait for us to do a few iterations. There we go, 12 iterations before it's going to actually print that we're part of the way through. And I bet this is going every 12. So there you go. And it's giving us a time estimate, again, around 2 minutes. In fact, it looks like it's maybe a little bit faster than previously. I don't know if that's the printing of TQDM was sort of slowing it down, or just using a for I loop for the training loop, actually. I guess that would be my hypothesis. We've accelerated this training loop now, which we've done in the past. We've accelerated the steps of the training loop in the past. Now we've done the whole training loop. But the big improvement performance-wise that we might be getting from this is that we could actually be jitting this. We're not jitting though, so what's going on there? Let me see. Actually, we could jit, but I'm pretty sure that for I loop is going to automatically jit the body fund for us. I know scan does that, and I think for I loop is sometimes implemented in terms of scan, so I think this should be working. We could maybe check the JAX docs to see if that's the case. So let me see if I can find any reference to JIT here. Yeah, so note, for I loop compiles body fund. So while it can be combined with JIT, it is usually unnecessary. So there we go. So for I loop also involves JITting. One consequences of this is that you can't use for I loop on code that you would not be able to JIT for some reason if you sort of have some sort of thing that's not traceable, like the kind of things that we're going to talk about next lecture. But what this means is that without even thinking about the performance of this loop, we were getting some extra performance for free. So maybe I would say that it's the jitting of the forward of sort of the individual step here, which is involving, doing autograd and stuff like that. And now this autograd is only happening once, and that might be leading to a speed up in the actual iterations of these loops, and we're getting a slightly lower estimated time. Although I noticed that, in practice, we're back to something like 2.5 minutes by the end. So, who knows? It's only on a laptop. It's a very small scale model. So these performance things are always a little bit hand wavy, but I would intuitively say that we'd be getting some performance improvement here. Some very slight performance improvement, I guess. Okay, so let's take stock where we're at. We've accelerated so previously to this tutorial, we knew how to accelerate parallel stuff with VMAP. Now we've seen how we can accelerate loops in JAX, which makes the compile times faster, even if it doesn't make the actual runtime faster. But it's essential that when we have very large loops, we're not generating huge redundant computational graphs. And these JAX loop primitives are essential for that. And we've seen an example of for I loop, and we've seen an example of scan. I think scan is the more commonly used one. The flexibility is extra sort of useful. You can do everything you can do with for I loop, you can do with scan. So it's not normally necessary to do for I loop. Normally I would just use scan, but at least you know how to use it. You've seen it now. And in future lectures, I think we're going to get a chance to use the while loop. So watch out for that. That will be interesting. But most of the time I'm using scan. So this was good. And this led to us being able to train a 1,000 layer DenseResNet in a matter of minutes without waiting very long times for compiling this huge computational graph. Remembering the computational graph issue is the main motivation for doing this loop acceleration because it's going to help the compiler know where our loops are. So there's one more thing I want to do in this demo, and we haven't had a very visual demo today, and that is going to change now. So I want to sort of set this from 1000 back to like 200 because I think that's going to be a good balance between performance and showing off that we're doing something kind of deep, and that will help for the visualization that we're about to do. So what we're going to do is we're going to implement another accelerated loop and then visualize it. What I want to do is we have this DenseResNet, and what it's doing is it's sort of taking this MNIST image and projecting it into 128 dimensional space, the embedding dimension. And then every step, it's adding some residual to that, which is going to move this vector around in this high dimensional space. And eventually, it's then going to make a classification. So but it's doing this computation like a very uniform way. Every layer is going to do some small change to the position in this big space. And if you thought about like the entire batch going through this big space or the entire training data set, it's kind of going to be moving them around this space. There'll be like a cloud of points. Each point represents one image of an MNIST digit. And then the layers are going to be like with just linear transforms and nonlinearities, kind of moving them around in small increments using this residual format. And then we're going to end up with like a cloud at the end of all of the things. And then we need to learn a linear decision rule based on that. And so it would be nice if what we could see is if we could maybe watch this cloud going around, and sort of as we go through the forward pass, where do these points move in this residual space? And then we can sort of see the classification being made at the end. And so what we'd like to do is capture these activations as we go through the forward pass and return those so that we end up with the trajectory of these points through the activation space. And once we have the trajectory of those points, we can't visualize it in 128 dimensions, but we could probably manage to visualize it in 3 dimensions using dimensionality reduction like PCA, and that's what pcax is going to be for in this code. And so now I want to sort of set up to do this, and also this gives an opportunity to show off some 3D plotting in the terminal with matthewplotlib, which I'm pretty proud of. So let's talk about how we would capture these activations. Now this is a chance to use scan and scan's output feature specifically. So what we want is we want to be able to get all of the activation vectors from all of the 128 dimensions, but all of the 200 steps in the forward pass. And so along with the actual prediction, I want to output this trajectory of vectors in 128 dimensions of 200 times. So I want to write a new function on my model that is not only going to do a forward pass, and so I'm going to copy this is the init, this is what I want, this is the forward. I'm going to copy this, and I'm going to say, what about forward with activations, or just forward activations. And then it's going to take the same input, self and image, but instead of just returning a single float for the predictions, actually, I don't know if I even need the predictions, but I will take them just in case. I'm going to return, in addition, another floating point array that is going to be 200 by 128, or in general, depth by 128, or depth by width of the network. And so what I need to do is when I'm going through this scan, I need to actually capture the activations at each point and return those. So we don't have to worry about the first activation. I'm not going to bother capturing that. Actually, you know what? I will, because I did it in my sample, so I might as well. I've got the code prepared to do it. We want to make it 201 because there's 200 layers, but we also have the initial embedding as sort of the first activation, and we might as well include that. This will be similar to when we were adding, in the overture, when we were adding something to the when we were concatenating the sort of initial state, and then we had the next states coming out of a scan. So here, instead of just returning none, I want to return the actual X. And then here, I'm going to get all of the X's, which I'm going to call sort of activations. And let me see, this is actually activations after the nonlinearities, after adding to the residual stream, which seems good, because this is going to be the trajectories of these points through the residual space. So we compute our R's, including putting them through the nonlinearity, and then we make a difference, and then this is going to be the updated value of X, which we pass through as the carry, but now we're also passing it out of the scan. So this is like, one more time to the whiteboard, just to very quickly sketch. When we had our scan, remember we had this idea that we're sort of computing down, and we have the carry coming in, and we have the input coming in, and we can have, our f function, and then we can have coming out the next version of the carry, and also coming out, we can have an output. And so this is going to be X, which goes forward to the next layer, and this is going to be capturing that X and making it part of an output array of all of the X's that we have from any time in our loop. So that is what's going on here. And so what we have here is this activations. Now what I want to do is actually also capture the embedding. So I better call this embedding something else, or capture it. I'll just say embedding equals X. And so then, because I'm not mutating anything, by the way, later, I'm just copying and overriding this variable, this embedding vector will stay the same. And then at the end here, I can unembed, and I've got the probs, and then I can concat activations. And I guess this will be all activations equals jnp.concat concatenate. We give it the list of things. We give it the embedding and the activations, which is all of them but the last. And then we say we want to embed along axis 0. which is our sort of depth or time dimension. And the only problem is this is a 128 vector, not a 1 by 128 vector, so I need to add an extra dimension. I could do this with inops. A slightly faster way is just to do a none index in to get that extra dimension there. And this should be all activations. This should now be a float. This is now a float 1 128, and this is a float 200 128 array, and we concatenate them on axis 0, we get our 201 128 array, so I can return that all activations. Okay, so that is another example of scan. Now let's see the payoff of this visually, and we're going to need to do some coding with matthewplotlib to make that happen. So let me see, we've run our training loop. Now let's PCA analysis of trajectories, and let's see. Or I guess PCA analysis is not right. It's just PCA. Because A in PCA stands for analysis. So let's see what code we have to write here to make this work. So first of all, we're going to need some inputs. I could take a single input and do a single trajectory, but it would be much nicer to see this whole cloud at once, I think. And so I'm going to do that by taking an X matrix, which is going to be our first 1,000 things from our test set. So we have our X test, which is our 28 by 28. X test was 10,000 by 28 by 28, and so I'm just going to take the first 1,000 of the sort of the test set, and so we'll have 1,000 by 28 by 28. And then I also want to know the labels so that I can kind of color these things so I can see where different digits are going. So Y test, the corresponding labels, the first 1,000 labels. So this will be a Boolean 1,000 array. Now what I want to know what these trajectories are for these examples. And so I'm going to need to run this forward activations function on all of the examples in this test set. And so I could do a single example if I used forward activations. I could go model forward activations. Actually, this is going to return the predictions, which I don't need. Let me call that ypred or just y or just underscore y, I suppose. This is going to give me the predictions of x0 or something like that. How would I go over the entire batch? Well, that's a job for vmap, our sort of simplest of our loops, because this can happen in parallel. So jax.vmap of model forward activations, and then I want to pass in the entirety of x. I guess I can do it here. I can just say x. This is going to give me, JAX vmap is going to transform this function. Let's have a look at the function. JAX vmap is going to transform this function. Remember, we're using the one argument version of forward activations because self is already applied because we're doing self.activations or model.activations or forward activations. So image is the only argument. By default, vmap is going to add a batch dimension at the start. And then for each of the things in the pie tree of outputs, it's going to add a batch dimension at the start of that as well. So it's going to add, we're going to have 1,000 by 10 for our predictions, and we're going to have 1,000 by 201 by 128 for our activations, which is what we want. So back up to this part of the code. I'm capturing and discarding the predictions, and I've got Z. So let me just annotate Z here as float array. Was this one? Yeah, no, this 1,000 is different from the 200 from the 1,000 layers we had before. It's just a coincidence this is 1,000. We have float array here of 1,000, which is representing our sort of batch size, by 201, which is representing our time through the model. So this would have been 1,001 if we're using the 1,000 layer version. And then we have our 128, which is our residual dimension. I guess I should put this beforehand, so I'm sort of declaring the type of the thing before we define it. This is just annotating for our own uses. That's just for readability. Okay, so now let's do the actual PCA. So this is to sort of capture the activations. Now we have to use pcax to do the PCA. And so to do this, this dimension is not going to be enough. I want to take this cloud of points over all times and actually do PCA on the whole lot, dimensionality on the whole set of all of the points and all of the trajectories. So I'm going to need to combine these dimensions, and so I want to use inops for that. So Z combined is going to be equal to inops.rearrange of Z. And I want to rearrange, I'm going to need more space, I'm going to rearrange this. It's currently batch, and then depth, and then width, we'll call it. And then I want it to be batch depth in one axis, and then width. So this is now going to be a 1,000 or 201,000 by 128 thing, and we're going to do PCA on that. So the PCA transform is going to be, we can just use pcax.fit to Z combined. And then I only want n components equals 3. I just looked up the example in the pcax quick start to do this. And then I should be able to get my, now I should be able to, having fit this transform to compute the actual components of my Z combined matrix, this entire big cloud of 201,000 points in 128 dimensional space. I should be able to apply that transform that I've learned, this PCA, to the original Z data to get a 1,000 by 201 by 3 array. And so I'm going to call that array XYZ because it's just got the 3 components. It's just a 3-dimensional, it's a cloud of 3-dimensional points. Or I guess I can call it XYZs if you wanted to use that. And I guess it's going to be, you know what, I'm going to use this convention where you say the batch and then the depth, use these letters as subscripts or as like suffixes to represent the shape here. And this is going to be given by pcax dot transform of this with this PCA which we've computed. This is the fit, and then this is telling us which the directions we're sort of extracting and projecting onto, and then I'm going to pass this Z data in, and then this should keep the shape. This is just a vectorized, automatically sort of vectorized function that can take any sort of number of batch dimensions, and it will just work, I believe. So in this case, I'm giving it 2 batch dimensions, one called batch and one called depth, and it's giving me back a thing that I want that has the batch and then the depth batch dimensions. Okay, so we're nearly done. I would like to do a little bit more of a transformation here. So for plotting purposes, I'm going to actually need this XYZ in NumPy. So I'm going to I'm going to leave JAX now and just do some plotting code. And we haven't normally shown the plotting code, but I think this will be fun and maybe worth it. But I need it to be a NumPy array so that it will work properly with the code that I'm going to write. So I want to convert this XYZ batch and depth to a NumPy array. And then I want to standardize it in that, you know, sometimes when you do PCA, you get values back like on these axes, they're projected like to hundreds or whatever. And I want to just make sure that this is going to be between basically like -1 and 1 so that I know where in the 3D space this is going to be. And so I'm going to also standardize it with saying XYZ batch depth divided by np.abs of XYZ batch depth dot max. So this will take the biggest value in this, and unless all of these are 0, this is going to be a non-zero value. And where by value I mean like magnitude, so big negative values also count, and then scale by that so that the largest value will now be like +1 or -1 in any of the dimensions, any of the 3 dimensions of this, and then that will sort of confine the cloud to -1 to 1 cubed sort of volume for my 3D plotting. Now I want to do one more loop for today, but it's just going to be a Python loop. And it's going to be a Python loop for doing an animation. I want to say, what layer am I up to? Let's say, actually, let's make it not a while true loop. Let's make it for t in range like 500. I'm going to say, what I want basically is to have one step of the animation for each layer, but then I want to keep doing the animation at the last layer so we can see more of the cloud. And so I'm going to just say the layer is going to be for the first 200 steps, the layer is going to be the layer. And then beyond that, the layer is going to be, I guess this should be actually 201 steps. Sorry, for the first, let's say this, for the first 201 steps, let's make the layer the time. And then after that, let's make the layer 201. We'll just stick to that. And when I say layer, I guess I mean like which time point in this trajectory we're sampling. Okay, So then what I'm going to do is I'm going to do a 3D visualization. So I also want to use this time to determine what angle I'm looking around. So I'm going to sweep a camera around the visualization. And so I'm going to say angle is going to be equal to the time divided by, let's say, like 150 by 4 by np.pi, which will give us an angle in radians that is going to rotate around a few times. Actually, this would make it rotate faster. I want it to rotate a little bit slower. Is that right? Yeah, so for example, if I divided this by 500, that would mean that we go around 4 n pi like once. So we go around twice. Yeah, that sounds about right. So let's just do that. I'll say this is the proportion of the time that we've completed, and this is when we've completed the full proportion of the time I want us to have swept around 4 pi, which means 2 full rotations. That seems like enough. That means we're going to be rotating around every 250 steps once. Okay, so then the actual position of the camera is going to be np array. I'm just going to speed through this code because it's sort of some camera calculations. So I want the x position of the camera to be the sine of this angle, and I want the y position of the camera to be fixed as like a little bit up, and I want the z position of the camera to be 1.5 times np cos of the angle. And this is going to implement a sweep in the xy plane, and then we'll be sort of looking down from the z plane. And this is going to be a moving now camera. So I guess I could say we're sweeping the camera. And then I think we're ready to plot. Yes. So yeah, the plot now that we want to actually do is going to be the things from this layer. So which points are we going to plot? Remember we have this batch depth dimension, XYZ thing. So this is a, I guess, 1000 by 201 by 3. And if I want to just pick a single one of those 201 depth axes corresponding to this layer, then I would get XYZ batch would be equal to XYZ batch depth index all of the points in the batch, and then just the layer slice of that, and then all 3 of these dimensions, this XYZ axis, which I can omit that. Okay, that should help. And now I can actually run the matthewplotlib command and say plot is equal to, we're just going to put a nice border around it, and then the actual plot is going to be a 3D scatter plot. So mp.scatter3. And then I would like to sort of just add some default axes so that I can see this in 3D really easily. So I'm just quickly going to do that. So we use mp.x-axis 0 to 0.2, and then I'll make that red. And then we can do mp.y-axis 0, 0.2, and we'll make that green. This is going to add these little like lines to represent like which directions these axes are in, and we'll do the z-axis as well. mp.z-axis 0 to 0.2, and we'll make that blue. And then we actually want to plot our data, which I think I can just put in as xyz b, which is this thing that we computed here. But I guess, want to control the color of it. I guess I'll make it white as opposed to the other. I think white is the default, but I'll do this for now. Camera position, we already calculated is this p. And then let me configure a few other things. So the vertical field of view degrees, I think 55 looks kind of nice. The height of the plot in terminal columns will make it 36, and the width will make it 78, so that it fits nicely on my terminal. 78 columns. I think that's all. Yeah, so in the border, I can add a title, and I can say this is the PCA at layer PCA of activations at layer, and then I'll put in the layer, which we have as this layer variable. And this will put a nice title on my border of my plot. I think that is enough. I just need to now print the plot. And it's an animation. I don't want it to go too fast, so I'm going to go to set the frames per second as 50, at 50-ish, minus the plotting time. But this will do everything except for actually plot my plot. What I want to do is if t equals 0, then I want to print the plot, and otherwise I want to do this trick. So the first time I want to print, and the other time I want to do this. The other times I want to do this trick where I scrub the plot. We've seen this in other weeks. I guess I'm going to make this a format string. So format, scrub the plot, and then print the new plot. And because the plots are all the same size, this will scrub the old plot, even though plot is the new plot by now. Okay, will this work? Let's see. Oh yeah, I'm still doing 1000, so let's make this a little faster. Okay, so here's an interesting thing. I'm struggling to quit out of this because I think it is in the middle of running something on the GPU, and maybe it's not listening to the CPU, so we might actually just have to wait for this for a minute. And then I think when it gets to the end of this loop, I wanted to run it faster. But this is pretty fast. I forgot this was the 200. I thought we were going into a 2.5 minute thing. Sorry about this. I think it's going to quit now. When we get to the end of the loop, it will quit because we've accelerated the whole loop. So it's all happening on the GPU, and then it's waiting for that to run. Let's try again. 200. This is 200. This is not going to take too long. We just have to wait a little bit. While we're waiting, I'm going to just think about what we want to do next, and we can wait in anticipation. Yeah, okay, I've decided what I want to do next. And we're nearly there. It's taking a while, taking its time, taking longer than last time for some reason. Slowed down, maybe my CPU is getting a little bit busy. Indeed, recording overloaded, sorry. I hope that when this finishes, the encoding overloaded. Oh, okay. There's a typo anyway. All right. This is getting comedic. But while I'm fixing this, sometimes I wish I had a compiled language and I would not have to find out about typos after running a long computation. So I've just fixed this typo in the name inops. Hopefully the recording is stabilizing now. I just thought it would be nice if we weren't just printing all of these points in the same white color, but if we could somehow print them in a color that represents the actual ground truth label, which is why we got these ground truth labels. So I can do that. What matthewplotlib will need to do that is it just needs a vector of colors here. And so you can get a vector of colors quite easily. And in fact, it's going to be the same colors. Colors equals, we have this y vector. That is going to be the indices that we need. If I divide that by 10, then it's going to give me numbers between, like, instead of 0 and 9, it will be like 0.0 and 0.9. And actually, I guess I want to divide by 9 because then that will give me a range between 0.0 and 1.0. And then I just got to put this through a color map. And so I'm going to use the cyber color map, which is sort of the cyan and magenta color map that we've been using. And then that is going to be sort of length 1000 vector of RGB triples. And that will be perfect for putting in here with our 1000 points from this time step of the trajectory. So let's do that and then see if we can run this one more time, and hopefully the CPU is going to be able to finish it without overloading my recording, and we'll see a pretty animation. Taking its time. wouldn't necessarily have to do 256 iterations. Nearly there. Runs much faster when I'm not recording. But then you wouldn't get to see it. Come on, you can do it. Come on, little MacBook Air. Okay, we're done. PCA. No more bugs, please. Hey, there we go. Hey, look at that. We're building a big cloud. We're spinning around. And I screwed up the indexing, but we saw it. It happened. You saw activations at layer 200. Okay, I do want to get to the bottom of this indexing issue. I think I was over-eager with this, changing this to 201. Of course, it has to be 200. The reason is because you can index an array of length 201 with an index of 200, but you can't index one with an index of 201. You can only do length minus 1 as the maximum index because we have zero-based indexing, of course. So how could I make that mistake? I want to see this one more time, but while it's loading, I'm going to describe the challenge. So the challenge for this week is we've learned all about accelerating loops in JAX. And I mentioned that, once we've accelerated the training loop, that opens up a door of we can suddenly run that training loop. We can VMap that training loop. We can do other things with that training loop and run multiple training loops in parallel. And that is really cool. So one of the things you might want to run multiple training loops in parallel for is you might want to do a hyperparameter sweep for your model to find the best hyperparameters. And so it would be cool, I think, if you could take one of the convolutional networks that we ran previously and see what changing the learning rate does, for example, and see if you can try multiple learning rates in parallel and evaluate them in parallel. So you would have to go to that old code that we wrote last time, accelerate the training loop with a JAX scan or whatever, or JAX 4i loop, and then run that parallel hyperparameter sweep. Okay, excellent. Here we go. So we're spinning around a few times. This is the cloud of all the points. You can see sort of different clusters of color that represent the different digits. And we saw it kind of in the first 200 iterations of this. We saw it going through, and now we've reached the end of our 500. We saw it kind of going through and expanding through this space. And that is something really cool about a deep residual network. And so I've left you with a challenge of taking what we did today and accelerating a training loop from one of our previous examples, and then you might have to use scan or 4i loop, and then you should be able to have a function that you can put through VMap that trains an entire model end to end. And so have fun figuring out how to do that and do a hyperparameter sweep. And I'll see you in the next lecture. Bye.